Today on the bench, ICOM's communication receiver ICR7000 with receiver problems. Welcome to TRX Bench. Okay, so this receiver works from 25 megahertz up to 1.3 gigahertz. It has been built from approximately 1986 up to 1990, and we have been told that something is wrong with VHF receive. So receive will be very low in the VHF area. So let's see if we have the same finding, and then we can go ahead and look what's really going on here. Okay, so the communication tester is connected to the radio, and I am injecting minus 93 dBm, which means this should be an S9 level. I mean, we do not really know if our signal meter is good, but anyways, with an S9 signal we should not hear any noise. And if you hear the signal, it is clear that that is not what it should like. So it seems that really something is wrong here with VHF. So let's here change to our communication tester so that we see the figures. Okay, and as I said, minus 93, which is an S9 level on our ultra short wave bands. So with starting from VHF up to SHF, we have another definition for what will be an S9 level, and so here minus 93 should be S9 compared to shortwave, where minus 73 is S9 level. Okay, so what we see is that our synod is too low, so it should be more than, let me say, 25 or even better, 30. It always depends a little bit on the radio, especially when we are testing for synod, because remember, synod always means it is signal to noise, and we are evaluating the distortion as well. And if we only have this low synod, that always means that of course our distortion is very high, and you can see it here. But anyways, we see our signal is not very good. So let me here increase my signal until we have a good synod level, and you see, okay, let me go up to 50 dBm, so that is really a very strong signal. And you see our synod level is not going over 22 dB even with this high level, and that is telling me, so let's double check here. Yeah, we have really still a very high distortion level, which is not normal, and therefore let me check the signal to noise value. Aha, and you see signal to noise, so without the distortion component we are much higher, and that could mean that we are out of frequency a little bit. So back to synod, and let me hear a little bit, not my output level, so I just wanna change my frequency here a little bit. So on the radio I have dialed in 145 290, and I'm interested if we are able to change our synod, if we are changing our frequency. And what you see, so what you see is, now back to signal to noise, and signal to noise is 34 dB, back to synod, and now we are at approximately 32, and we are off frequency. So let me see if we can go even higher. No, it's dropping. It is dropping. And now where we have approximately 32, we can track our distortion level, and now it is more or less on a normal distortion value, and that is telling me that the complete receiver is out of frequency. So you see there is a delta. That means that our reference oscillator and maybe a local oscillator or whatever we have here inside is not on frequency, so that we are beneath our wanted frequency. So now you see 32, so let's go back here to 145 290, and here it is. So that is a frequency which is dialed in at our radio, and you see our synod has dramatically dropped. Compared once again to signal to noise, it is 33, and that is absolutely telling me that really our frequency is off. Okay, so that is for sure, and it is for sure that our sensitivity is not in spec. Okay, and our specs are telling us that on FM, and we are on FM, with 0.5 microvolt, we should be able to reach 12 dB synod. So that means we are going down now to 0.5 microvolt on our generator, and minus 0.5 microvolts is minus 113 dBm. So we are dialing now minus 113 dB in, and what we want to see is a synod better than 12 dB. Okay, so let's put in minus 113 dBm. That was wrong. Minus 113 dBm, and here we are. And you see we are completely in the noise, so nothing at all, so we are not able to receive a signal. So now let's increase our level until we are reaching 12 dB synod. So let me go up, and you hear here in the background our tone is coming up, and you see now we have, yeah, it is jumping a bit, so that is normal if there is a noisy signal. So maybe, yeah, something here, maybe here. So minus 95.5 dBm. Yeah, and the delta between minus 113 and minus 95.5 are 17.5 dB, and that is really a lot. So really a lot. what's here our receiver is not able to deliver. So therefore there is definitely a problem on VHF. Okay, and we are now here on UHF 430-100 just to see if our receiver is working here just fine, and you see it is definitely directly much better. But anyways, let me go to minus 113 dBm, which is here, and yeah, that is very clear. What we can see is that we are better than 12 dB, so that means that we are definitely having this portion working just fine. So we are better than spec, even with our reference frequency problem, because when I test here, do we here see, yeah, and you already see it again, that we have here a difference, a huge difference between signal to noise and SYNAT. So even here we see the problem with our reference frequency. But anyways, we are easily reaching our specs, so that means we really have a problem on VHF and VHF. UHF is working just fine. And here, just for our reference, on 28.500, so 10 meter band, also with minus 113, and you see we are simply able to get our 12 dB out of the radio, so that is obviously fine as well. That is definitely telling me that the lower portion of the radio is working as well. And now let's have a last view on our 1 gigahertz area, or better said on the SHF band. Yeah, and I'm feeding 1297 here into the radio, and let me here increase the level, but for any reason only noise, so that obviously means that our SHF band does not receive at all. So that means obviously that we have two problems. We have problems on SHF, so you see the 1 gigahertz is here switched in, and you see the red 1 gigahertz indication, and that means it is 1297 megahertz, our frequency, and you do not hear nothing, so our generator is still here connected to our radio, but the only thing we have is noise. So that means we have here a complete breakdown on this portion of our radio. So okay, we see what the problems are. We start with VHF, and let's have a look what's going on there, and then we can go over to our SHF area, but let's start with VHF. Yeah, let's first have a look here on our block diagram to discuss where we start. and as we can see here, we have here our antenna, and then we have here a through connection on our main board. So this is the main board, and we have here a mixer which is obviously for our higher frequencies, SHF, I believe, so we have to double check that. So we have a through connection here, so looks like that we have two relays involved. Then we have here attenuator 20 dB in, and then we have four band filters, yeah, 4 band filters, and you see this first one is from 25 up to 90 megahertz, so that is a lower frequency area, HF and 50 megahertz mainly, and then we have 90 to 250, so that is our VHF area, and that is the area where we have the trouble. And this is here our UHF, where we know that it is working, and Q4 here, our band pass filter is from 512 up to 1 gigahertz. And we know that we have here in this area and in this area a problem. What we can say so far, that as we have a fully working receiver on UHF and on, let me call it shortwave, shortwave and 50 megahertz maybe, so we know this both portions are working fine and our receive is fine, so that means that all the other portions of our receiver seems to work just fine. I mean, apart from the problem that our reference frequency is off, so we need to adjust maybe down here. Can you see it? Let me have a look. So maybe here, this is obviously our, where is our, so this is all mixer, maybe this one here, is this here our reference oscillator? Don't know right now, we will find it out later. Must be here somewhere, so that needs to be adjusted for sure, so that is what we know. But beside that, we know that we have a problem obviously here in this portion, and for SHF, yeah, maybe something is wrong here. So we see we have here two contacts as well, which are most likely relays as well, and of course maybe that this portion here, this converter is not switching in, or that here maybe our oscillator for our first mixer for SHF is not working. So that is what we need to check. But as long we know that with our through connection, our shortwave 50 megahertz and UHF is working fine. As we said first, let's start here. Here on the left side of our radio we have our main board, and on the main board we have here this portion where we have here our converter, our frequency converter, especially for the higher frequencies as far as I see. But anyways, we have here two coax cable, and that is telling me that our through connection is here going over this portion, and here we have of course the rest of our main board, and that is mainly the audio circuit, and yeah, some adjusting components for volume and of course for squelch. So that is here on the main board, and we want to start on our RF board, where we get access to here from the top. So mainly we have here two boards. So this one here is the IF board, and this here is the RF board. And let me take off here our shielding, because I believe that we have our filters, our band filters here underneath this filter here. Of course, shielding. And here it is. So you see already that we have here our 4 sections, 1, 2, 3, 4, and that means that here the upper one is for shortwave and 50 megahertz. Here we have our VHF, so this is here UHF, and then this here must be our SHF portion. And we have here the both relays. So we have seen that for especially our higher frequencies, it get switched here with relays, and we have yeah, I believe this here must be our attenuator. And so the first step is to look after our VHF portion here. Okay, and so we will do. So let me zoom in here a little bit that we better see what's going on. So Q2 is our VHF portion. So we really need to start here, and where we need to start with are our voltages to operate this portion, this front end amplifier, if you like. And you see, of course, our Q2 is our front end RF amplifier, and we see here Bandpass filter 2, so that means we need to get a positive voltage here over this C125, and this is then supplying first our amplifier transistor. So you can see here over a Zener diode we get our supply voltage for our Q2. Additional to that, because it is a dual gate transistor, we get here on gate 1 a voltage which is, let me see if it is mentioned here somewhere. So do not really see. Here it is. So it is between, is it 1.5 to 1 volt, or is it, I don't know, I believe it is 1.5 to 1 volt, so somewhere in that range. So that looks like a gate supply voltage, gate 1, which we see is supplied here to gate 1, and the bandpass filter switching, which is supplying our transistor, is also supplying or doing our biasing for our switching diodes. So you see, as we have it always, we have here at the output the D18, right, which is our switching diode, and of course our D12 here, which is our input switching diode, and we know that this diode needs to get a bias voltage, and you can see it here. Our bias voltage is supplying here our D18, and then our let me see where it goes to ground. Yeah, here we can see it. So the D18 is here over the L20 and the R19. We have our loop closed, right? And the same we have here. Also again, bandpass filter 2, supply voltage here over the D12 and then over L9 to R1 to ground. So that means this loop is closed as well, and that then means that our diodes are biased, and an RF voltage which is very low for our circuit here. We know that with minus 113 dBm the radio should be able to show a synod of 12 dB. So, and that is, you know, minus 113 dBm is really a very low RF level, and that needs to go here over this and then gets amplified here in our Q2, and then it is leaving here our front end amplification and goes to the next circuit. Additional to that, and that is very interesting and important, so you see here over C126 another voltage which is here going into the circuit, and what we find here and there, so this are cap diodes which are is a moving bandpass filter. Okay, so we changing here the voltage with changing frequency. So if we are moving our input or main dial for frequency, then here over this, you can't see it, 1 second. So then here over this op amp, right, we are changing our DC voltage here to our bandpass, our moving bandpass filter, and that means that this bandpass filtering here, so at the input of Q2 and at the output of Q2, is finally adjusting the center frequency of our moving bandpass filter. So what we need is this both voltages, and of course this voltage coming here from our operational amplifier needs to deliver the right frequency for our test frequency, right? So this must be synchronized. Okay, so let's check for the voltages. So I've checked it before. Our bandpass filter voltage must be around 6 volt. So that is for switching here everything, and then our transistor gets approximately 3 point something voltage for its operation. So this Q2 is a gain or does a gain of approximately 10 dB, and yeah, so let's check these parameters to see what's going on. Yeah, and that is again the view here onto our bandpass filters. So we said that this is here for shortwave and of course for 50 megahertz, and that means this portion here is our VHF portion, and you see already here the 3 yeah, supply lines, let me call it that way, and on this supply lines we should find our different voltages, and that is the first what we are gonna check. Okay, so let's start. I need to connect ground here to our multimeter. Maybe is it this way a little bit better? Can you see then where? No, you can't see it. So maybe I have to put it down here, and now you can see what I'm doing. No, you can't. No, you can't see the meter. Ah, that is funny here. Okay, now it might be better. So let's simply start here with our left supply line, and here, yeah, that is what I already told you. This is here our bandpass filter supply voltage, and as well as the supply voltage for our Q2. The second one is our 12.8. Alright, so that is the supply voltage for our moving bandpass filter. And then this here 1.2 volt, so that is the voltage for our gate 1. And that means that all these three voltages are present. I'm now interested if we really can see our 12 volt moving, because now I go down, let me see, how can you better see what I'm doing? Not really good, maybe that way. So okay, so you see we have our 12 point, I do not get a good contact. So you see our 12.8 volt, and now when I start turning here my main dial, so you see that this voltage is moving down. So I'm changing here our RX frequency with the main frequency dial, and you see that the voltage here at our moving bandpass filter is changing as well, and that is a clear indication for our for the function of this portion. So the operational amplifier is obviously delivering a changing DC to our moving bandpass filter, and that is definitely right. The next step, what I'm interested in is whether this voltage is getting finally to our Q2. So first of all, let's check for our supply voltage, and that should be around 3 volt or something. Maybe that is, where is it? Can't find it here in the moment. Okay, let's double check. Okay, so once again, so this is our supply voltage for the bandpass filter itself and for biasing our diodes. And here, so this is here now our supply voltage for our Q2, and you see over the Zener diode we have approximately our 3 volt, which is just fine. And then this is here gate 1, and we are testing here our for our 1.3 volt something, which is obviously given. This is gate 1, so there is nothing, that is fine. And now I'm interested if I get here our supply voltage at our switching diodes, right? So if these diodes are biasing, so let me first check here our output diode. output diode is showing at its anode 5 volt, so that looks healthy, and at cathode we should see 0.7 volt drop, and yeah, we have approximately 0.7 volt drop, which is telling me that biasing is working. And the same we have to do at our input diode. So at anode we again, can you see it? I hope. At the anode we have 5.0, which is looking healthy, and at the cathode, let me see, here we have cathode and we have 4.2, which is telling me that the biasing is working for our input diode and for our output diode. So that all looks pretty healthy. Now I'm interested if our Q2 is doing its amplification, and as I said, the amplification is approximately 10 dB. So that means we should see at the output a level which is 10 dB higher than what we have at the input. Okay, and because we are dealing here with extremely low levels, of course we need to use our spectrum analyzer, and yeah, what we are doing right now, I'm testing the input level at our FET Q2. So let me see if I can get it here. Okay, I have to switch off modulation, so now I have only our carrier, and what you see is approximately minus 85 dBm. So I'm feeding here the system with minus 80 dBm, so we have a loss from the input over all the components of approximately 5 dB, and I have definitely here a testing arrow because I'm probing here directly inside the circuit, and that means I have always impedance mismatching. So 85 dBm looks fine at the input, no problem at all. And now I'm testing at the output, where we should have approximately 10 dB more. So let me put my probe here down to the output. Let me see. And yeah, it is minus 77, minus 76, something around that. So that is telling me that our little Q2 is really doing approximately its 10 dB of amplification. So that is telling me that the amplifier itself is working fine. We know that the biasing is given, we know that all the needed voltages are given to the system, so everything looks more or less healthy. Okay, and that means we have to look once again into our schematic, and yeah, we are seeing here at our dual gate FET that input versus output, we found that we have approximately our 10 dB gain amplification, which is just fine. And now we, you know, it looks like that really everything is healthy, but nevertheless we do not have our wanted sensitivity. So we have seen in our first test that we really are losing here quite a lot. And well, but according to our test results, I'm wondering if maybe here our given DC to our bandpass filter is on its right level, because remember, when we did the first test, we recognized already that there is obviously a misalignment, so that the crystal frequency is not spot on, and you know, this radio is 30 years plus, I believe, and that means that there could easily some more misalignments, so that we really need to take that into consideration. And therefore I wonder if the voltage we have tested here is really synchronized with our input frequency, because it is clear if our voltage here is on a wrong level, then our bandpass filter is out of tune, and that means that of course we are losing our signal with a wrong alignment here. So let me first of all, because before we go ahead, let me check if maybe our alignment is a problem as well in this portion of our circuit, because if that is the case, we really could search for decades and we never would find an error here. Okay, and yeah, let's double check it here. So my input frequency is 145,290, and I'm feeding minus 80 dBm, and remember, minus 93 should be an S9 level, so this is already a very strong signal, and therefore we have received here on our VHF band, but our sensitivity is given with minus 113, alright, and now this is minus 113, and you see we are completely losing our signal. I mean, let me go a bit higher here, I don't know, maybe minus 109, or I don't know, minus 108, so we need to find here a starting point. And yeah, I'm really interested what is really going on here with our moving bandpass filter. And once again, when I go down here, so for the moment in time, where was it? I believe here. So when we go down there, you see 12.7 volt, and I'm wondering if we change this voltage to another level, if then we could improve our receive. So therefore, let me simply inject this voltage externally from my power supply, and then we have the chance to adjust here our voltage for our moving bandpass filter, and let's simply see if we can adjust or improve our receiver sensitivity by moving this voltage. Okay, and therefore I have taken off here our lead, which is for our bandpass filter, and I'm now supplying it with our 12.6 volt, and I'm going now and change my voltage, and we will watch our incoming signal. Okay, so here we have all our figures, and what we see is that we have no signal with minus 108, and our 12.6 7 volt to our moving bandpass filter, and now I'm changing the voltage. So yeah, let me see, I'm changing it and watching the synod meter and listen. Look at this. Look at this. 16.6, and that is almost a nice signal. So let me go here down to, I don't know, we are almost there. Have a look. So minus 113. Let me see if I'm still able to improve our signal. I mean, anyway, so that is approximately 10 dBm. Not 10 dBm, sorry, 10 dB synod. Have a look. So no fake here or something. So let me go here to our power supply, and you see 8.6 volt. With 8.6 volt you see we are peaking just a little bit. Yeah, 10 dB synod maybe. And you see here my clamp is sitting here onto this wire, and now, I mean, this is not a idle situation. This external voltage, and as we are talking here about capacities, it should hold for a short moment it charge, and therefore let me simply take here it away. Yeah, that is incredible. So have a look. Sorry for this camera work, but under this condition I think you will forgive it. So you see, now it is just fine, and now the synod is dropping because we have no power supply connected to it, and we are losing the charge in our caps. So that is a reason why it is dropping down now. And when I now put my power supply back, so give it back a little charge, and here it is. So charge is back here in our caps, and you see that it is working. Yeah, and the conclusion is that we have no hardware problem, so there is not a faulty component somewhere. It is simply an alignment problem, and that is a little bit what I already thought. So we have seen that there were problems with our crystal and so forth and so forth, and thus this is not unnormal, I would call it. It is yeah, it is really an alignment issue, and before we go ahead in any way we need to perform alignment so that we have a good status where we can work on. Alright, and therefore I have already opened here my PLL unit, because that is where we start up, and therefore let's do our PLL alignments. And I had to dismantle it a little bit more so that we get access here to this little, looks like a compartment, and down here somewhere our test point must be for adjusting here our crystal frequency, which is 36 megahertz. First of all, we start with the maximum level, which is first we will adjust, and that should be 100 millivolt peak. So let's do that first. Alright, and the first test, as I said, is the output level of our crystal, or better said, it is the output of the tripler, because the crystal is 12 megahertz, and we are testing behind the tripler circuit. That means we are reading, or should read, 36 megahertz, but apart from that we need minimum 100 millivolt peak. Okay, that is the signal, and if I zoom in a little bit, then you can read the value down here. So our voltage peak is more than 100 millivolt, so we are reading 196 or approximately 200 millivolt. So that means our level is just fine, so we do not need to adjust this. But now I have to go ahead with all the other settings, and yeah, I come back if I have an interesting finding. Okay, so after adjusting some levels here from our LO outputs, we have now to adjust for frequency accuracy, and this here is our first test on the second LO output frequency, which should show 768 megahertz, and what you can see, we are approximately 10 kilohertz out. So this is 100 kilohertz, this is a 10 kilohertz, and this is 1 kilohertz. And as this is 0, we are approximately 10 kilohertz too low, or if you like 9.5 kilohertz too low, and that is already much if it comes to frequency accuracy, and that is what we have seen. So first we have now to adjust this here to exactly 768. Okay, so let's try to bring it in, and yeah, so what you see is we are getting closer, and that is what we need. And you see, by the way, this is something which really takes a while, so you have to do it here with a little patience, as you can't rush, otherwise it definitely don't work. So therefore, really step by step, and then you are getting close to your final result. But yeah, it is a little bit unlucky that we do not get a tolerance here. So our service manual is not telling us about the allowed tolerance. Well, anyways, we are close enough, I believe, and now I have to go to the next step. Yeah, and also our LO frequency 1 needs to get adjusted a little bit, not that much, we have here approximately 400 Hertz, which it is off. So it is it should be 923.7 megahertz, and you see 400 approximately. So let's try to adjust it out a little bit, wrong way, and you see we are getting closer. So this is always the same. As I said, it takes time. Be patient if you're doing something like this, and yeah, that should be close enough. Okay, so we have all alignments done here to the PLL, so that part is ready, and we can go ahead. I did an additional alignment of the 10.45 megahertz here on the IF board, which is done as well. So what we can say so far, all frequency adjustments has been done, apart here from our gigahertz section, and good enough that the next step here in our alignment procedure is now the main and doubler unit. And you may remember when we did our first test and we switched in here for 1 gigahertz, we were not able to receive anything. So we know that there is a bug, maybe in the doubler circuit or so. And now it is a good step to simply follow our alignment procedure for the doubler circuit, which is here on our left side. We have here our main board and our doubler circuit, and we simply go ahead in our alignment procedure, and while we are doing so, we can also troubleshoot our filter and our mixer and whatever we have down there, to see if we find a problem here, and maybe we easily find why we are not able to receive on the 1 gigahertz area. Okay, just to remember where we are, so this is here our PLL board, and that is what I've shown you already closed with the shielding, and that is what we have done so far. And as I told you as well, so we have done here our IF unit, and on the IF unit we did here our 10.245 megahertz alignment, and here as well our 456 kilohertz and 453 kilohertz alignment. So that has been done, and now you see we are approaching now here our doubler circuit. Doubler circuit is on the main board, and yeah, so that is now the point which or where we can do our trouble shooting together here with our alignment procedure, and therefore let's see what we have. Okay, and that we all know where we are. Here again our block diagram, and you see here is our RF unit with our bandpass filters, where we already had worked on, and where we will do in the next or over next step our moving bandpass filter alignment, which is very important, we have found. And Yeah, we have done our complete PLL section, so let me have a look here once again. So you see here we have done all these alignments on our PLL board, alright, and now we are on the main unit where we have our doubler circuit on, and when we switch our 1 gigahertz button in, then you see the relay 4 and the relay 3 switching, and we get here our mixer circuit in, which consists of our high pass filter, an RF amplifier, and then our mixer. And on the other side we have here our crystal, and then a tripler and a doubler circuit, and then here again our mixer, and then we are able to convert our higher frequency signals into a lower signal that it can then again here pass through our bandpass filters and can treat it that at the end of the chain we are able to receive our voice or music or whatever, but normally on a communication radio it is of course voice. Alright, so that is now the area where we need to troubleshoot a little bit, because we have seen that it did not receive, and therefore if we go through here and check here if our signals are there, and if the higher signals are getting through our mixer and so on, then we might get an idea what's going on, and maybe we are able to find our problem during our alignment process. Okay, and this is the main board with our doubler, mixer, and whatever circuit, and what we find here. So this here, and I've already taken off the shielding. So this is here our doubler circuit. Here we can test if the signals from the crystals are coming through. This here, on the other hand, is our high pass filter, and when we zoom in here a little bit, you see down there this guy here. So this is our RF amplifier, and then the incoming signal from the antenna has to go through our high pass filter, gets amplified here by our little RF amplifier, and then gets here to our mixer block, which is called our IC9. So this is here the mixer, and from our doubler circuit we should get from the output 1 gigahertz towards here our mixer IC9, and that simply means if I supply a signal in our 23 centimeter band, let's say 1.297 megahertz, then we get of course our 1.297 now gigahertz. Before I said 1297 megahertz, which is the same than 1.297 gigahertz, which comes here in our circuit and has to pass through here our amplifier and high pass filter, and is then present here at our mixer, right? And from our crystal we need here our 1 gigahertz at the output of our doubler, and then 1 gigahertz and 1.297 mixed in this mixer means that we have a signal which goes into our bandpass filter on the RF unit of 297 megahertz, and then we can work on the following signal path with this 297 megahertz, which is much simpler to handle than this high frequency. So therefore, let's simply step here into our alignment process, and let's see what we find. Okay, and our alignment procedure is telling us that we should test here at C2, which is it C2? No, it is C1. We should test at C1 because that is the input here of our doubler circuit. We should test for 500 megahertz, okay, and it should be approximately 0 dBm. So that is what our service manual is telling us. Okay, and let me go down here to L2, and you already see that here we are. So that is our once again C1. So that is the input of our doubler circuit, right? And let's see if we take here our peak, and you see that it is a little bit out. That is interesting. So here in the center is our 500 megahertz. So we should see our carrier right here in the middle. So it is off, and it is really off a bit. So we have, yeah, it is 8 kilohertz something. What it is off, we will see it later. It is really quite a lot. 2.4, yeah, approximately 7.5 kilohertz. It is off, and that is quite a lot for a reference oscillator, because remember, we really need a very, very precise carrier, otherwise the mixing process might go wrong. So therefore, okay, it is there, and we have approximately our 0 dBm, so everything is fine. And what we want to check right now is here at our where is it? Can you see it? Let me double check. Yeah, here at the output, so which is down there. Don't know if you can see what's written on the PCB. Now you can read it. So W1 is our output test point, and as it is our doubler circuit, we should see 1 gigahertz down there. Okay, so let me go down here to this test point, and yeah, let me show it on the screen. Okay, and here it is. So we have a good level. So let me set here our cursor, and you see it is 11.8, so approximately 12 dBm. So our schematic is telling us should be around 10 dBm, which is fine. So we can say so far our amplitude, our level is just fine, but again what you can see is we are out. So 1 gigahertz is right here in the middle, so that is the center, and you can see that we are out approximately what is it, 15, approximately 15 kilohertz is our carrier out or off, so that definitely needs to get an alignment, but I'm quite happy to see that our carrier is there and that it is on the right level, so that is just fine. Okay, and our manual is telling us that our frequency alignment pots or filters or caps or whatever are down this shielding, and this has been soldered. It looks like that already somebody was in. I would not believe that it looks like factory. I don't know, whatever. So we need to take the shielding off to get here down to our adjustment pots or whatever. But before we do that, we can simply test here our input from the antenna. I'm really curious if there is our input signal present here at the output of our high-pass filter, because then we would know that both signals are really getting here to our mixer. So that is important to know. So now we need to feed in our signal from the signal generator, and then we can test if the signal is going through here to our mixer. And to have finally a strong signal, I'm feeding in my 1.297 gigahertz with minus 50 dBm, which is quite a strong signal, and I should easily be able to test it out. And therefore, yeah, let's go to the unit and check if we can see this signal. And we are testing here at this capacitor our input signal, and then we can test our output signal down here. So basically it is behind our RF amplifier transistor down here, and let's see what we can find. Alright, so this is here our input signal, and okay, let me put my marker here onto it. And you see we are quite exact on frequency, so 1.297, which is quite nice. We are feeding in minus 50 dBm, so we have a loss of approximately 3 dBm, which is just fine with this high frequency. And here testing here with open shielding and what have we. And so that is definitely just fine. So we know the signal is at the input. And now let me go here to the output of it. And here we are. So that is quite nice. So you see we have the signal at the output. You see that our frequency is accurate, so no problem. What you see else is that the little RF transistor is amplifying by approximately 10 dB, which is fine. So what we can say so far is that everything is fine. So we know that both signals, so the crystal signal and of course our incoming signal is present, and I believe it is present at our mixer circuit. And we found that we did not get a receive signal, and I have already an idea, but let me put the camera in a better position for you. Alright, so here's our unit, and you see we have dialed in here the right frequency, and you see the 1 gigahertz information is on, so everything is fine. Our generator is sending with minus 50 dBm into our receiver, but you see nothing at all. So modulator is on, so we should hear our 1 kilohertz tone, but nothing. It is absolutely quiet. No information here on our S meter. So simply it is a kind of disaster. It is not working. But remember, we had our crystal oscillator, and especially behind the doubler circuit where we had our 1 gigahertz signal, right? And we have seen that it was out approximately 15 kilohertz, and 15 kilohertz is really a huge difference. So maybe our unit will receive if we adapt here our frequency on the dial, because then maybe we get our receive signal through our receiver. So let's see. I simply go up by 1 kilohertz. Let me see. Yeah, generator is definitely switched on, and my deviation is on, and 1 kilohertz is on as well. Have you seen that here? So I'm cranking up to 4, and something happens here with our S meter. Okay, so let's go up a bit more. You see a signal is coming up, and do you hear that? We have a signal, and now, yeah, let me turn it down. Now we have changed our frequency by 5 kilohertz, but we have seen that our 1 gigahertz signal from the doubler circuit is approximately 15 kilohertz away. So let me simply crank it up here. Hey, have a look. Have a look. So it is receiving just fine. No problem whatsoever. So here, these are our 15 kilohertz where we have seen our generator of internal generator. Fine, it is receiving. So that means most likely if we have done our alignment to our generator here, to our crystal, whatever, I have to double check it, but we can adjust, of course, our frequency, then this 15 kilohertz will be gone, and we should be able to receive our signals right on frequency. Now I'm interested if the sensitivity is more or less given. So let me simply go down to minus 113 dBm. And of course we will have noise in the background. But you still hear the signal. I'm not measuring the sinus right now, but you easily hear our test tone in the background. And here, have a look onto our generator. So no fake or something, minus 113 dBm. So that means that our receiver is here fully in spec. And that means, yeah, let me open the shielding here on our adjustment elements, and then let's see if we can dial in our crystal to the right frequency, that this problem is gone. And here is our circuit open, and our frequency control is this little adjustable coil down here. So we have to adjust it here, and let's check on our counter that we can really do this frequency adjustment as accurate as possible. Alright, and here we have our output frequency from our doubler circuit, and here again it is proved that we have our 1516 kilohertz where it is off, and that is what we really need to get to the right frequency to have our 1 gigahertz area, or our 23 centimeter portion back working. So let's try what we can do. I hope I have the right adjustment tool here, and yeah, you see we are able to crank it up, and yeah, after a couple of years it is changing, of course, and it is normal that an old radio needs an alignment. Yeah, so let me finish it here, and then we go ahead. Well, our frequency is not really able to get to the 1 gigahertz, which we of course need. So our range is finished at approximately, yeah, you can see it, 995, which means we are still approximately 4.5 kilohertz out, and well, that is an aging problem. So remember, this unit is really quite old, and of course some of the components are aging, and our correction circuit to get here this crystal in the right frequency is this little coil and this capacitor. So that is a series resonance circuit or loop, or however you want to call it. And now I'm really here at the end of the range of this coil, and we're still missing 4.5 kilohertz, and that means that maybe we need to change this little capacitor. So our service manual is telling me that it is a ceramic capacitor, so that makes it a bit easier, because normally we have meeker capacitors down here, because you know, they really need to be stable, and a ceramic capacitor is not that stable, but in this configuration it should work, and therefore, yeah, I have to take the board off completely, that I get underneath, and then we need to try to change here a little bit the configuration to get up to 1 gigahertz. And here we have the board flipped over, and surprise, surprise, so another sign that obviously somebody was already in. And yeah, you know, that can be really a nightmare. So okay, I have to take off the shielding that I get access to my little capacitor, and then let's see what I can do. Alright, here is our new capacitor, and I will get it in so that we are able to change our range a little bit. I mean, it is not much anymore, but it is still a bit, and therefore, yeah, let me get it in, and let's see if we then will be able to obtain our 1 gigahertz. Okay, so still not under control. I mean, I was able to pull the frequency more or less to 1 gigahertz with this little capacitor, but the problem with these oscillators is if you change too much the series configuration which is connected to our crystal, then you're able to pull the frequency where you need to have it, but on the other hand you are losing gain, so our amplitude is really going down, and we need approximately plus 10 dBm to have enough gain that our mixer work. And if this gain is too low, then it sounds like you are losing sensitivity, right? Because you need a certain level for your mixer, otherwise it doesn't work, and that's a problem right now. So we were able to pull it to the right frequency, but then we were approximately minus 30 or minus 40 dBm, which is much too low for our local oscillator gain. So that was obviously not the best idea. So I've put the original back in, and I have now changed a little bit the capacitor in the feedback circuit in our oscillator configuration, and I have put in here, you see this, a trim cap. So with this configuration I'm able to increase our gain, and also I'm able to pull the frequency to the right frequency, which is of course our 1 gigahertz, and I still have enough gain. So I have now with this configuration, so this is now what is it, a 30 picofarad variable capacitor, and with this cap I'm able to adjust for 10 plus 10 dBm, which is the needed level, and then I was able to, you can't see it, and then I was able to pull here with my coil down here. I was then able to pull the frequency spot on 1 gigahertz. So this configuration with this little cap works, but now I have the problem that I do not get this big component here into my circuit, because the space I have is really very limited. So you see it down here. So this here are our both pins, and I'm really not able to get this big component in. So this here was the original. So this is a Mica 47 picofarad cap, yeah. So now I have here the challenge to get it somewhat managed to have this variable cap here in the circuit. And if I have a solution for that, then I guess we can use our circuit once again. I mean, this will not change the aging problem, and I believe it is most likely here our crystal which was really aging a lot, maybe due to heat problems, and well, it can be that it will work for a couple of time with this circuit adaptation, but it also can happen that it will drop down completely. So then we need to change this crystal, but you know, to buy a new crystal, if you can't get it as a spare part from ICOM, it gets really very expensive, because then this crystal frequency needs to be produced, and it is a 55.555, so 555 megahertz crystal, and you can't easily buy it everywhere. But anyways, we try our best to get here our adaptation somewhat working. As I said, I know I'm able to get 10 dBm, which is fine, and I'm spot on 1 gigahertz, so perfect. So now I need to solve here our space problem. Okay, but let's see test results. So what you see what we have done. Okay, so I'm now here, come on, I'm now here at the output of, I have a little issue here. Okay, so now I'm at the output of my doubler circuit, so which is 1 gigahertz. I'm losing always the signal here. Come on. Alright. Alright, so now you can see it, and let me put the peak onto it, and you see it is positive 10 dBm, and it is spot on 1 gigahertz. So yeah, I should not get away here from my test point. It's a little bit tricky here, so just that you see I'm not faking here anyhow. So it is really here my circuit, and I'm probing here at our doubler circuit as we have done it before, and you see that we are really spot on 1 gigahertz. That is great. So now let's see if we can solve our space problem. Okay, so I have tinkered here a little bit around, and yeah, what you see here is an SMD cap, variable cap, and I've put it here onto a piece of PCB and soldered here some little wires to it, and now I try if I can get it here into our circuit somehow, right, here down there, and if that is somewhat possible, then we are lucky. First of all, I have of course to take off here our bigger component, so you can see here that we really have here different sizes. Both are 30 picofarad, but this is a conventional one, this is a SMD part, and I hope that I will be able to get it somewhat in here. So let's try. Okay, and as you can see, I was able to get here our trim cap into our circuit, and now if you're lucky, we can adjust it and everything is fine. So let's hook it up and let's see. Alright, so I'm here at our double output once again, and let's directly go over here to our analyzer, and what you see is this is our 0. Let me go over, then you can see the scaling, and you see where 0 dBm is, and we have a nice output at positive 10 dBm, which is awesome. Alright, now I let the circuit warm up a little bit, right? I let warm it up just a little bit, and then I hook it to the frequency counter to dial exactly to 1 gigahertz, okay? Okay, now our counter is on, and you see we are approximately 400 hertz too low, and I try now carefully to adjust it here, and you see I'm able to dial it in, and yeah, this is now again extremely sensitive and touchy, but you see this is our 1 gig, so our circuit is still not completely hot, but you see I'm easily able to tweak it to 1 gig with this modification. So that means I will put now the circuit back into the circuit to get it completely heated, and when it is completely heated up, then I'm going to do this final alignment once again, and then our 1 gigahertz LO is working just fine. So that is awesome. Okay, so all is back here in our radio, and radio is now running for a while, so that everything is on temperature, and I put here the lid on a little bit just to get here the right temperature to our components, especially to our crystal, and now we can do our final frequency alignment. Alright, so let's start here, go down to our test point, and here we are. So we have to tweak it a little bit, but that will be no problem anymore. So let's see what we can do here. Alright, so you see I've already put the resolution up to the maximum, so we are losing our 1 on the left hand side, so that is on overflow. So our little LED under the last digit is telling us overflow, means that I have maximum resolution right now, so that means we can read the frequency down to 1 Hertz, and that is important here, as we really need to be as best as possible on frequency. And you see it is very touchy, which is normal, so this has to be done very carefully. And you see now it is fine, so this jump is more or less normal. We should not forget that we are pushing up the frequency from 55 megahertz up to 1 gig, and all the arrow will be multiplied if we are testing at our 1 gigahertz test point. So now we are off approximately between, let me say, between, so this is 10 Hertz, and you see this is an arrow we can live with, so this is no problem whatsoever. So this is really just fine. So normally you would not test this frequency with this high resolution, so this is just fine. Okay, so then let's test if we switch on now here our generator, and let's see. Yeah, so that sounds good. So let me put down the radio that you can have a look onto it, and I just do it here without changing anything, so you really should see that here the frequency is absolutely set to the right frequency. So you see now the radio is working just fine, even in our 23 megahertz 23 centimeter band, so everything is just fine. So our S meter needs to be aligned a little bit, so that is not finally good, but that is something we will do at the end. Now we go ahead on our RF board to align our moving bandpass filters. Okay, and we go ahead with our bandpass filter alignment, and you remember that we took off here the wire, and we fed here some external voltage, and then we were able to finally get receive. And now I'm here at already at the checkpoint for bandpass filter alignment, and let us have a look in our service manual for what values we have to look out. Okay, and I directly start here with our bandpass filter in the VHF area, and therefore it is this portion here we have to align. And I have already connected here my voltmeter to diode 51, and with this both frequencies we have to, you can't see it, we have to adjust our bandpass filter with R71 and R73. Now I have dialed in 90 megahertz, so this frequency, and I should test at D51 for 90 megahertz 1 volt. Alright, and I show you what I'm already testing there. Okay, and here it is. So we should read 1 volt, okay, and we read 5.7, so that is clearly showing that it is completely misaligned. But let me check the second voltage at 150 megahertz. So 150 is dialed in, and we read 13.3 volt, and we should read 8 volt, and that is exactly what we found. Our voltage was definitely too high, and that was the reason why our moving bandpass filters are out, and we were not able to receive our signal. So therefore, let's try if we are able to get our 8 volt if we adjust our R71. Okay, so let's go down to the pot, a little bit lower here the noise. Okay, so let me go down to R71, which is down here, and let's try if we are able to go down to 8 volt. So let me see, there we can go down, and oops, no, I'm not able to go down to 8 volt. So hey, what's going on here? Something is obviously wrong. Okay, that means we need to have a look here onto our schematic. And you see here, where is it? This one is our D51, right? So that was our test point. And let me zoom it in a little bit that you can better see it. Yeah, once again, so here is our D51 where we test it, and you see our voltage is directly coming here out of our op-amp, and here is our R71, and we are more or less adjusting here a little bit it is finally a DC amplifier. Yeah, I think that it is, and we can adjust here with this both pots our voltages in a range, and well, it is which IC is it? It is IC1, and we need to supply, of course, our IC1. So let me see, it is here 0.4. So let me see what it is. Okay, so our supply voltage should be 24 volt, and the minus point or pin is -7. So let me check here if the voltages are there. Okay, so I'm now really interested in our supply voltages. Let me take here this clamp out, and it is J8, which is down here. So let me see what we can find here. 14.4. The next one is 8.9. Yeah, so that could be our 9 volts. So the next should be -7, which is right, and the next one should be -12, which is -14, which is a little bit too much. But this is funny here. So we only read 14.4 volt, but it should be 24. Alright, so something is wrong here. So we are missing 10 volt, and that could be the reason why our op-amps are not really delivering the right voltage for our moving bandpass filters. So let me see where this 24 volt get produced. Okay, I found it. So it is a DC-DC converter down there. And yeah, I've again down here our output pins. And yeah, so let me show you once again the meter. And this pin here again should be our 24, and it is only 14.4. The next pin is +9, which is fine and within tolerance. The next one should be -7, which is fine, and the next one should be -12, which is -14.4. So 2.5 volt too much maybe. So that means something is wrong down here with our DC-DC converter, and I've already taken off here the shielding, and you see we have really a bunch of electrolytic capacitors in there. And if there is in a DC-DC converter which is producing a wrong voltage, so that always could mean that something is wrong here with our capacitors. I mean, they are really getting hot. So when I just touch here our housing, I feel that it is really warm. And yeah, the radio is approximately 30 years old. So that means that we really could have some of these capacitors which are dried out. So what we need to do is we have to take it off and see if we get access here to our circuit. Okay, so I've taken it out, and I'm interested if our input voltages are fine. So this side is output, and here is input or supply voltage, if you like. And let me see if we can get both somehow. Not really. Let's see. No, that's the best I can do, but maybe this way. So this should be 13.8, which is fine. The next one should be what is it, 9 volt, I believe. I can't read it. Yeah, this is 9 volt. The next one should be -7, which is -6.9. So that means everything is fine if it comes to the input side, and we only produce our 24 volt and our what is it, minus 12 volt here in our DC-DC converter. And yeah, I have to take here the shielding off, that I get access here to the board, and then okay, I can do some additional tests. Yeah, I'm working here on the DC-DC converter, and of course, first of all, it is important to check the capacitors, and I have here really one capacitor analyzed, which is completely high impedance. So let me show you that. So that is a capacitor, and it is 139 kilo ohm, which means that this capacitor can't really work in the circuit. And yeah, so normally I would say we really have to replace all capacitors, because starting troubleshooting without changing this capacitor is always a nightmare. But I was really interested to see if I find the problem by really probing. So normally it is quite clear. I would really swap everything, and then I would do another approach. But yeah, sometimes it is interesting to see if you really find the problem. And yeah, this capacitor is a problem, much too high. In the impedance should be something 0.2 or so. So let me go ahead and see if there is another capacitor doing this garbage, and if not, let me only replace this for testing. So that is very important. Yeah, and it is pretty much always the same. So they are using capacitors with 85 degrees C, which means that capacitors are really jeopardized, and then most likely cheap brands. So now I've replaced them with Panasonic capacitors, and well, let's see what our voltages are now showing up. Okay, so let's start with the first one, which was around 13, and yeah, have a look. Now it is plus 22, and our schematic is telling us that it should be 22, which is fine. Also, it is called the output is called 24 volt, but in the schematic is mentioned 22, so that is fine. So the next one is our plus 9, which is fine. The next one is our minus 11, which is fine as well. And the last one is minus 11. Yeah, minus 11, which is fine as well. And this one, what was minus 7? Yeah, minus 7 is fine, and minus 11 is fine. So that means our voltages are back, and again, due to dried out capacitors and DC-DC converter without working capacitors is always a problem. So now everything is nice, and we can check if now our op-amp will be able to set to the voltages which were requested for our bandpass filters. Okay, so I'm back at my D51 for our bandpass filter, where we really had the sensitivity problems. And Yeah, let's see if we are now able to get it tuned to the right voltage, so that the bandpass filter can really follow the frequency. Okay, so first I have to dial in 150 megahertz, so that is already done. And on 150 megahertz I have to adjust here my pot to 8 volt, so we are on 2.7. And you remember that we were not able to get it dialed in with a faulty DC-DC converter. Okay, and now let's see if it works. Looks pretty good. Okay, here we are. So we can leave it that way. So that is 8 volt. It's dropping a little bit, but yeah, you see that is a reason why it is not always advantage to have so many digits. Sometimes it is more confusing than anything else. Anyways, so that looks fine. Now I have to change my frequency to 90 megahertz. So let me see. Now it is connected to 90, and let's see. I should adjust it to 1 volt, and it is R73, which should be that pot here. Okay, so let's see what I can do here. And yeah, looks great, looks really great. So I'm really able to adjust it to 1 volt. Yeah, that is normally fine, but okay, so let's see if we can do it a bit better. Yeah, you can see what that makes for a difference with the working DC-DC converter. Now our op amps are able to work correctly, and that is the result. So the third point is I have to dial it to 249 megahertz. So let me do that. 49 megahertz, which is dialed in. And yeah, so display at 249, that is right. And approximately where is it, 17.5, so we read a bit more, but I think that is not really the problem. So that is approximately what they are stating in the service manual, so that is fine. More important is that with 150 megahertz we have 8 volt, and yeah, so that is really very nice. So next step is we want to see if now our sensitivity is back. Okay, and we dialed in exactly the same frequency where we did our first test with, so 145 to 90. And let's see what we have on our on sensitivity. Yeah, and here you can now see the improvement. So really on 145 to 90, right, with minus 113 dBm, which is the level given in our service manual, we are able to peak 20 dB synod. So you see that is really excellent improvement. So now it is really working just fine, and 12 was the requested synod value, and we are much better, really much better than that. So I'm sure I can go much deeper. Where is it? Maybe here. So I can go down to minus 117, which is a lot. Remember, dBs are not linear, so that is always a logarithmic value, so it is really a lot if you can go down from minus 113 to minus 117, and you are approximately getting the requested results. So, you know, that is awesome, and that is telling me that our radio is really back in service. What I have to do finally here is that down here we have all the op amps, which are responsible here for our moving bandpass filters, and yeah, I have to check if all are adjusted in the right way. I mean, we didn't really recognize it, because even with the broken DC-DC converter, our third filter, bandpass filter, was working just fine. So there we didn't get the full problem, but I believe that now with the new DC-DC repair, this filter will also be better, and I will go through now the whole alignment procedure for all of our bandpass filters to really get the optimum out of the radio. But I don't do it on camera, because it is now exactly the same procedure, and I really do not need to show it once again, as yeah, it's the same. Okay, so everything has been done, so all bandpass filters are adjusted. So it was only a little bit where I had to adjust the other bandpass filters, so they were more or less spot on. I did here the S-meter adjustment, and I did sensitivity adjustment on the IF board, and some other alignment points I followed along. So I can say now everything is working just fine. You see it is again running here on 1 gigahertz. I'm really happy that I was able to get the local oscillator adjusted or modified a little bit, so that the radio is also working in the 23 centimeter area. All the other areas are working also just fine, and we are in all different bands better than the required sensitivity given in the service manual. So finally I really can say this radio is back in service. Everything is working just fine, and yeah, so I'm really at the end of this video. It has taken a little bit longer as expected, because I didn't expect to have to do some modifications and repairs. I really thought it is only a setting, but you see how it goes. So sometimes there is more behind a fold than you expect right from the beginning. Okay, so that's it for the day. I hope you enjoyed this video a little bit, and if you really like it, please give me a thumb up, and Thank you for watching and catch you next time. Bye!